Every single second, the living world around us takes a collective breath. Millions of species, from the blue whale in the deep ocean to the microscopic bacteria in the soil, and 8 billion humans are continuously consuming an invisible gas, oxygen. It is the molecule that fuels our thoughts, ignites our fires, and drives the metabolism of almost all complex life. By all logical accounts, we should have run out of it millions of years ago. Yet the air we breathe remains locked at a steady, life-sustaining 21%. How is this possible? In this documentary, we will go on a planet-wide journey to solve this great scientific mystery. We will discover why the common explanation that trees simply make our oxygen and we breathe it is actually a profound scientific misconception. By connecting deep geological history, molecular biology, physical oceanography, and satellite data, you will realize that your next breath depends on a hidden, planet-scale trapdoor. Every breath you take is a connection to a vast invisible system. As your lungs expand, you inhale a cocktail of nitrogen, trace gases, and a highly reactive molecule that makes up precisely 21% of our atmosphere, oxygen. We take this percentage for granted. It is the Goldilocks zone of our planet. High enough to sustain complex, warm-blooded metabolisms, yet low enough to prevent our forests from spontaneously combusting. But if you look at the sheer scale of consumption, a paradox emerges. Every animal, every fungus, and nearly every microbe on this planet is constantly inhaling oxygen and exhaling carbon dioxide. Even the rocks themselves absorb it, rusting away under the open sky. By some estimates, if all oxygen production stopped today, Earth's atmospheric oxygen would be completely exhausted in just a few thousand years. So, why has our oxygen supply remained incredibly stable for hundreds of millions of years? The answer lies not just in the trees above us, but in a delicate, hidden ledger kept by the Earth system itself. A ledger that connects the highest mountains to the deepest marine trenches, and is monitored today by an armada of satellites in space and robots in the deep sea. The standard story we are taught in school is simple. Plants are the lungs of the earth. Through photosynthesis, they absorb carbon dioxide and water, use sunlight to build sugar, and release oxygen as a waste product. It is an elegant, closed loop. But there is a catch. When a tree dies, it decays, The mushrooms, bacteria, and insects that decompose its wood consume exactly the same amount of oxygen that the tree produced during its lifetime, turning its organic carbon back into carbon dioxide. Even when a leaf drops and decays in autumn, the process of decay inhales the oxygen that leaf breathed out in spring. Respiration and decay are the mirror images of photosynthesis. If every plant that grew on land decayed completely, the net oxygen produced by the land biosphere would be exactly zero.
To find the real engine of oxygen production, we have to look past the forests, past the coastlines, and dive into the open ocean. Here, drifting in the sunlit surface waters, live trillions of microscopic organisms, phytoplankton, algae, and marine bacteria. Among them is Prochlorococcus, a photosynthetic cyanobacterium so small that millions can fit in a single drop of water. Yet these marine bacteria, along with other phytoplankton, are a key part of the global ecosystem, producing more than half of the oxygen we breathe. To monitor this ocean engine, oceanographers at institutions like the Woods Hole Oceanographic Institution operate global networks of robotic instruments. These are the Argo floats, an array of nearly 4,000 autonomous robots drifting across the global ocean, diving to depths of 2,000 meters to record the physical and chemical properties of the water, including its temperature, salinity, and dissolved oxygen. By integrating this physical data, scientists can track how ocean warming and circulation affect the marine organisms that generate our air. But the ocean too is subject to the law of the closed loop. When phytoplankton die, they are eaten by marine animals and decomposed by deep-sea bacteria, which consumes the dissolved oxygen in the water. If all marine organic matter decayed in the water column, the net oxygen produced by the oceans would also be zero. Yet here is where Earth's hidden trapdoor opens. About 0.1% of the organic carbon produced by photosynthesis escapes decay. Before deep-sea microbes can decompose it, this organic matter is buried beneath layers of seafloor sediment. By burying this carbon, the Earth prevents it from reacting with oxygen. This is the master switch of the global oxygen cycle. Because the carbon is locked away in a geological vault, the oxygen that was split from water during photosynthesis is left behind, free to accumulate in our atmosphere. Without this geological vault, a planet can lose its breath entirely. Look at Mars. Billions of years ago, Mars may have had water and an atmosphere, but Mars lacked the tectonic and sedimentary cycles necessary to bury carbon and recycle minerals on a global scale. On Earth, the burial of carbon is a continuous process driven by plate tectonics. As tectonic plates collide and slide beneath one another, they carry sedimentary rocks deep into the mantle, locking carbon away for hundreds of millions of years.
When oxygen began to accumulate on Earth over 2 billion years ago, a transition known as the Great Oxidation Event, the planet's oceans literally rusted. Dissolved iron in the water reacted with the newly produced oxygen, depositing thick layers of iron oxides on the sea floor. These red banded iron formations are the physical, geological monuments of Earth's first global breath.
If carbon burial produces oxygen, what keeps it from rising infinitely? If oxygen levels rose to 30 or 40%, wildfires would ravage the globe, destroying terrestrial biomes. The system has a built-in thermostat, rock weathering.
When mountain ranges are uplifted by tectonic forces, they expose ancient sedimentary rocks to the elements. These rocks contain fossilized organic carbon that was buried millions of years ago. Rainwater and atmospheric oxygen react with these exposed minerals in a chemical process called oxidative weathering. This weathering consumes oxygen, turning the ancient buried carbon back into carbon dioxide. It is the long-term geological scale balancing act. Carbon burial produces oxygen, while rock weathering consumes it.
To understand how these massive systems interact in real time, we must look at Earth from space. Today, programs like the Copernicus space component operate advanced Sentinel satellites that continuously image and measure our planet's vital signs. Through the Copernicus land monitoring and climate change services, these satellites track global vegetation levels, land cover changes, and soil moisture. By mapping these biosphere variables, scientists can calculate the precise rate of global photosynthesis. But space observations are only half the story. To ensure accuracy, these satellite measurements are validated on the ground through in situ calibration supersites, forming a cooperative open science network that spans the globe. For hundreds of millions of years, this planetary balance has held steady. But today, human activity is introducing a new variable into the ledger. By burning fossil fuels, which are nothing more than ancient buried carbon, we are bypassing the geological thermostat. We are artificially accelerating rock weathering, combining buried carbon with atmospheric oxygen at a rate millions of times faster than natural geological processes. According to reanalysis data from the Copernicus Climate Change Service, the concentrations of key greenhouse gases have reached record-breaking heights, with carbon dioxide averaging 419 parts per million and methane reaching 1,902 parts per billion. While this fossil combustion consumes oxygen, the atmospheric reservoir is so vast that we are in no danger of running out of breathable air. However, the warming caused by these greenhouse gases is warming our oceans, reducing their capacity to hold dissolved oxygen and putting immense strain on marine ecosystems.
The 21% of oxygen that fills your lungs at this very moment is not just a static physical property of our planet, it is a dynamic, living system. It is produced by microscopic organisms in the sunlit waters of the ocean, preserved by the subduction of plates deep into the Earth's crust, and regulated by the erosion of mountains over eons of geological time. Every breath we take is a whisper of an ancient geological pact, a reminder that on this fragile blue planet, everything, absolutely everything, is connected.